Homework 14, Rational Functions, video number 1. In the previous videos, we've looked at quadratic functions, which were parabolas. We looked at polynomial functions, which could have a variety of end behavior and wiggle a lot in the middle and cross the x-axis or touch and turn around. And then we looked at some division and synthetic division things in an effort to find zeros of polynomial functions. In other words, solve longer equations equal to 0 by finding a good division problem with the remainder of 0. To conclude the material that's going to be on test 3, we are going to take a look at what are called rational functions. And by definition, a rational function is just a function of the form f of x equals p of x over q of x, or p of x and q of x are polynomial functions. In other words, just take two of the things we've been working with and stick them on top of each other. For example, we could say f of x equals and write any polynomial function on top of any other one. It can be a short one like 5x plus 2. It can be a much more convoluted one like x cubed plus 7x minus 4x minus 28. But the size of the functions really doesn't matter, or rather the degree of the polynomial functions doesn't matter. All a rational function is a ratio of polynomials. Now, what's different about graphing these guys versus graphing just a polynomial function? Two things in particular. Number one, because we have denominators, we have domain issues. There are numbers we're not allowed to put in some denominators because they make them equal to 0, like this guy. Putting 2 here would be bad, or putting 1 here would be bad. And because these functions have points in the domain that you're not supposed to go to, I'm not supposed to put in 2 here, I'm not supposed to put in 1 here, over here. It's supposed to be squared. Yeah, have fun putting this equal to 0 and solving it. But if you solve this equal to 0, I believe that you'll get 2, -2, and -7. Go ahead, try it. But I digress. There are certain points that we need to avoid, and these points can invoke something called a vertical asymptote. Now, in the next video, I'll give a strict definition of what constitutes a vertical asymptote and how we locate them, but I just want to quickly show you what they look like. A vertical asymptote, there's a P in there that's hard to pronounce, is an imaginary vertical line that a graph would approach but not cross. So for example, this function's graph looks something like this. We'll talk about how to get there in a few videos. But there's an imaginary vertical line that when this function approaches, it either goes downward forever, or in this case on the other side goes upward forever. So we're going to figure out how to locate those. I kind of gave you a not so subtle hint when we talked about domains. But in addition to vertical asymptotes, rational functions might also have what are called horizontal asymptotes, which is exactly what you would think it would be. It's a horizontal line. Now this one also has a vertical. In fact, both of these have a horizontal and a vertical. But it's a horizontal line that as a function gets further to the right or further to the left, it approaches. So the further out we go to the right, it gets closer to this horizontal asymptote. And as we go further to the left, it also approaches that horizontal asymptote. And in a few videos, we'll discuss how to locate those. But I just wanted to give you a brief introduction to rational functions, what they are, and they have issues when it comes to graphing.